In 1936, Alan Turing demonstrated a hard, absolute limit to mechanization. Turing analyzed computation by reducing it to a finite, rule-governed procedure, a sequence of explicit, local steps that a machine executes blindly. This analysis proved that no single set of fixed rules can solve every possible mathematical question. This boundary is famously formalized as the halting problem. Given a description of a computer program, no single static algorithm can reliably determine whether that program will eventually stop running or if it will loop forever. It represents a strict mathematical wall. Yet modern artificial intelligence relentlessly consumes tasks once thought to require unmechanizable human intuition. Language translation, complex game strategy, and sophisticated pattern recognition are routinely executed by machines today. If finite rules are permanently bounded by Turing's mathematics, the expanding capabilities of AI create a direct tension with those limits. Resolving this tension requires us to view intelligence as something other than a single static algorithm trapped inside one fixed set of rules. In his paper, What is Intelligence?, researcher Chien-Ping proposes that intelligence operates as a mathematical limiting process. AI progress follows a recursive, step-by-step formalization, where previously uncomputable tasks are continuously absorbed into settled, rule-governed procedures. To model this correctly, we use Turing's own advanced framework for relative computability, the oracle machine. An oracle machine executes ordinary computation, but can query an external oracle for answers to specific problems beyond its own internal rules. This oracle represents the structural upward displacement of human specification. When a lower-level task is automated, the work of defining rules and judging success moves to a higher level of the system. Human intelligence currently serves as the benchmark driving this continuous sequence, providing the open-ended pressure required to mechanize each new step. This diagram starts at ordinary computation, Turing's empty oracle, A0. Mechanizing a system establishes computational layer C of A, where a machine operates strictly by fixed internal rules. Proposition 1, local closure, dictates any internal procedures remain permanently trapped within it. Proposition 2, local incompleteness, ensures every layer leaves behind an unsolved relative boundary. This is the Turing jump, A'. Representing the relative halting problem, it sits entirely outside the machine's computational reach. John Searle's Chinese room argument highlights this. A system following fixed symbolic rules lacks true understanding. It identifies the boundary of a single static layer. While a single AI model is mathematically bounded, the broader system can break through to the next level through structural revision. Historical progress avoids the impossible requirement of instantly solving the full Turing jump. Instead, progress occurs through step mechanization, generating a step witness, a newly formalized computational layer strictly stronger than the baseline. Mathematically, this new layer, AN+1, is strictly stronger than the previous layer, but remains strictly weaker than the full Turing jump, A'. When execution inside a layer settles, the difficult work of specifying rules and evaluating outcomes is forced upward. This upward displacement is a historical constant. Tasks manually done by human computers were encoded into programs, requiring higher-level languages and sophisticated compilers to manage. Each successful step mechanization automates a previously difficult task, while simultaneously relocating the uncomputable frontier to a higher level of specification. We can mathematically connect the process of human-guided system revision to this hierarchy of Turing degrees. Consider a one-level stable revision process. This occurs when an algorithm produces a sequence of updates or corrections that eventually stabilize on a fixed output. This feedback loop is the engineering equivalent of the relative limit lemma, the mathematical bridge connecting iterative stabilization to higher-order computation. Theorem 4 establishes that if an iterative revision stabilizes, the outcome corresponds exactly to computation in the Turing jump, A'. Finite internal updates, like running a program multiple times, remain within the base layer. However, when a sequence of updates converges through continuous correction, it officially raises the mathematical degree of the system. When an engineering process identifies a stable correction to a model's behavior, it effectively computes a value at the next Turing degree. This structural stabilization identifies meta-level correction as a formal ascent up the Turing hierarchy. Once a newly established layer reaches A', it encounters its own relative halting boundary, requiring the process to repeat. We model this using a two-level nested stable revision process, effectively a system that evaluates the evaluations. Theorem 5 proves that a two-level nested revision corresponds to the second Turing jump, A'. Nesting the revision process allows the system to climb the stack of boundaries. This creates a progressive, infinite computational sequence where each successive layer is stronger than the last. Modern AI architecture mirrors this theoretical tower. Base models are directed by prompts, refined by reward models, and overseen by human developers. The true architecture of intelligence reveals itself as an endless recursive tower of increasingly powerful, stacked computational layers. The ultimate object of this framework is the whole process oracle, HO+. The whole process oracle represents the entire historical sequence of all AI step mechanizations. It is the infinite join of every computational layer ever achieved. Proposition 4, whole process non-capture, mathematically proves that no single finite layer can compute or contain the whole process oracle. The part can never encompass the whole. Analyzing a static snapshot of an AI model will always fail to measure its true trajectory. Intelligence exists in the transitions between the layers, rather than in the isolated code. Human intelligence provides the structural pressure driving this progression of step mechanization. Intelligence functions as a continuous, historically formalizable process of navigating through relative uncomputability.